Welcome to physics. It is time to ponder lenses. So we built kind of the background on refraction, gotten an idea of how light bends based on index refraction, calculated angles with Snell's law. Now, I want you to think about a lens, whether that be in eyeglasses or anytime you have seen a lens. We want to define a lens, but we want to define it in terms of the characteristics of what it is. So think about the shape. Think about what makes a lens a lens. If a substance is going to behave as a lens, first of all, it's going to have to be transparent. The fishbowl over on the side with the cap behind it. The fishbowl and the water inside are transparent. But not only are they transparent, but the sides are also curved. And by the sides, I'm referring to the front and the back. Any lens, if you think of feeling a pair of eyeglasses, it's not just a flat piece of glass. If it was, it would be a window, but it has curvature to it. So a lens is anything that's transparent and has sides that are curved, but there's a little bit more to it. It also has to vary in thickness when you're moving from the front to the back. So it can't be the same thickness, otherwise it would be just like a window. It has to have places that are narrow, places that are wider. So in general, we define a lens as anything that is transparent, that has sides that are curved, and that varies in thickness. So traditional lenses are made of glass, but a lot of other things also behave as lenses. Welcome back to the physics classroom. It's a little bit quiet here these days, but we're going to ponder a couple demonstrations on refraction. Let me explain what I'm going to do, and then I'll turn the lights off. So what I have set up here is basically a box that's emitting light, and it will emit rays of light that go across this sheet of paper that you'll be able to see when the lights are turned off. Okay, I'm going to take several different pieces of glass and put them here between the rays and the paper so that you can see what the shapes are doing to the rays of light. So I've got a big rectangle. I've got a semicircle. I've got a shape that is thicker in the middle and thinner towards the outer edges. Nope, not going to set that one up. I'll set that one down. I've got a shape that is thin in the middle and thicker towards the outer edges. And then I have some various and assorted different smaller shapes. But basically what we're trying to deduce is what happens when light goes through these. How does it affect the direction of the light so that then we can work towards an understanding of lenses and what lenses are and what they do and why. So now hopefully you can see those rays of light traveling across the sheet of paper. Right now I have nothing between the ray box and the screen. If I run my fingers across there, you can see how it interrupts the light. So now what I'm going to do is going to take the rectangle and put it in front of the light. Notice the direction of the rays there versus here. When you have this rectangular shape, okay, the direction of the rays of light really don't change. They get interrupted a little bit, but they're traveling essentially in the same direction without the block as with the block. If I now switch over to the semicircle of glass, when I bring the semicircle in, notice what happens to those rays of light. They go from being reasonably parallel to each other to coming down to a single point. That single point that the rays of light come down to would be known as the focal point. So we have a shape that is thin at the top, thick in the middle, and thinner at the bottom, and it's causing those rays of light to come together to a single point. If I take another shape, that is wider in the middle and narrow at the outer edges, notice it also causes the rays to come together. The focal length would be a lot longer on this one than it was on the other one, but it still causes the rays to come together. If I take the circle of glass and put it in front of here, notice what happens for the circle of glass. You get the rays coming together, but they come together extremely quick, really close to where the circle of glass is. This would be an object of a very short focal length. Now let me change over to something that is narrow in the middle and wider at the outer edges. Notice what it does to the rays of light. Causes them to spread out. They're originally parallel, and now those rays of light get wider apart. Now I'm going to switch to another shape that is narrow in the middle and wide towards the outer edges. When I bring it in here, notice what it does to our rays. The rays start parallel, and then the rays spread apart significantly. So in summary, if you have a shape that is wider in the middle and narrow towards the outer edges, it will cause those rays of light to come together. If you have a shape that is narrow in the middle and wider at the outer edges, it causes those rays to spread apart or diverge. That's how we're going to classify lenses, by where they are thickest based on what they do to the light. Based on the demonstration, we can now classify the different shapes of lenses as converging or diverging. In the demonstration, we saw that light traveling through a lens that was thicker in the middle caused that light to come down to a single point. That's what converging means. So then we call these lenses that are thicker in the middle converging lenses. Conversely, we saw the lenses that were thin in the middle, the glass shapes that were thinner in the middle and thicker on the outer edges, to cause the rays to spread apart. So lenses that have that thick part out towards the outer edges we call diverging lenses. Now, introducing a little bit of terminology. On your converging lens shape, we saw in the demonstration that the rays of light passed through the lens and they came down to a more central point. That central point where those rays converge to is going to be the focal point. The focal point of the lens is the point where parallel rays converge to. For a diverging lens, those parallel rays went through the lens and they went apart. Well, as they went apart, if we can follow those rays back, like your eyes would, those rays would have appeared to have initiated from a single location, and that would be the focal point of that diverging lens. So for a diverging lens, it is the point where parallel rays appear to originate from. Now, let's think a little bit in terms of what causes the light to do that. So if we draw a shape that is thicker in the middle and thin towards the outer edges. So imagine this to be round, and I'm just showing you a cross section. What we observed when light went through there is light got to the lens, and after it came out the other side, it went inward. If I draw another ray here, light went through and it refracted out the other side and came to a single point. Now, let me give you an analogy. Here is our shape of our lens again, but use your imagination for a minute. Imagine that you are out in a field, and in this field, no social distancing, you're with a bunch of friends. So I'm going to draw you and a bunch of friends. That's the top of your head. There's your friend, another friend, another friend, another friend, etc. And you're all holding hands. I'm glad you have a good imagination. And not only are you holding hands, but you are running this way in the open field. Now, as you run that way, you approach a very large mud puddle. Now, this mud puddle has kind of an odd shape to it, but it's very muddy, several inches deep in terms of the mud and water. So your line of people, you're running towards it, and when you get right about to this location, some people are going to go through the mud, and they have a larger distance of mud to go through. Some people have a very short distance of mud to go through. Well, your nice straight line isn't going to be nice and straight on the other side, because those that had to go through the longer section of mud are going to fall behind those that went through the short sections. So when you come out the other side, your people are going to be in a shape like this. Now, our people are an analogy for a wave. So here comes our wave into the glass. And what happens is it slows down when it goes into the glass. And the part in the middle slows down for a longer period of time than the part on the outer edges. So when that wave comes out, it doesn't come out straight, but it comes out curved. And once it comes out curved, it continues that curved movement and focuses down to a single point. So our lens works because the glass slows the light, and that combination of the slowing of a light and the variety of the thickness of the glass cause that light to come out, and in this case, focus down on the far side. Now, if we now replaced our lens by a diverging shape, because the shape we've been analyzing is a converging shape, imagine that to be your mud puddle. And now your line of friends that are running at that really weird shaped mud puddle, when you get to that mud puddle, those that go through the thicker part, which now would be towards the outer edges, are going to lag behind those that went through the thinner part. So then coming out the other side, you're going to have people approximately in this shape. Now, if this is a wave, here comes our wave. That wave comes out the other side, and the center leads the outer edges. As that wave then continues to travel, it spreads out looking like it had originally started from a single point on that side, and that point would be called the focal point. So again, the why behind lenses working is a combination of their varying in thickness and the change in the speed of the light. Now, a little bit of terminology. Here I have converging lens and diverging lens. Principal axis, that's a line that's going to go through the center of the lens. On that line, we're going to identify several different points. F is your focal point. 2F is a distance of twice your focal point. So, because the light can go through either side, we're going to have an F and 2F on each side. O at the center, that's just referred to as the optical center of the lens. And then for reference, we put a plane down the middle. In a simulation that you'll do, they will simulate specific rays that will travel. So I want to summarize a little bit about those rays. So I'm going to draw a converging lens shape. We know it's converging because it's thicker in the middle. I'm going to draw our principal axis, and I'm going to label our different points we saw on the previous slide. There are an infinite number of rays that come off of an object, usually by reflection unless it's producing light. So there are some rays that you have to use multiple calculations of Snell's law, and some rays that are easy to predict where they go. And so I'm going to draw a light source, and we can imagine an infinite number of rays coming off of that light source. Now we're going to follow a few particular rays. I'm going to take a ray, drawing from the center of my object, straight across, parallel to the principal axis. Well, we saw in the demonstration that a ray that is parallel to the principal axis, it will refract, and when it does, it goes through a point that we define as the focal point. So that's an easy ray to draw. Realistically, there is a bend at each one of the surfaces. I'm going to simplify it to a single bend at the lens plane. For reference, we're going to call this a parallel ray. A second easy ray to draw is kind of reversing that logic. So I'm going to take another ray, and I'm going to take it now initially through the focal point. The other ray started parallel and went through the focal point. This one went through the focal point, and it will refract out parallel. So for reference, we're going to call this a focal ray, or sometimes a principal focus ray. One more ray that is easy to draw, and that's a ray that will basically bend and then unbend. It bends as it goes in one side, and it unbends as it goes out the other side. And that ray goes toward the optical center. It will bend as it goes in and unbend as it comes out the other side. And so for name reference, we would call that an optical ray. Now, notice those rays went through the lens, they refracted, and they all came together right to a single point over there. Well, that is the location where we would see the image of whatever our object was. That image forms where refracted rays intersect or appear to intersect. In this case, the rays actually intersect. And because they actually intersect, that would mean this is a real image because the light actually goes there. Remember, with reflection, we talked about real images and virtual images. When the ray actually goes there, it is a real image, and this is something that could be projected onto a screen. A virtual image is an image formed where the rays do not actually pass. In the case of reflection, that was behind the mirror. We will see some virtual images also with lenses. Now you're going to move into an investigation whereby you're going to move objects around and see how the rays that we've drawn actually go through the lens to be able to form that image. And then you're going to describe that image as upright or inverted, reduced or enlarged or same size, real or virtual. So it's all a part of a simulation. Then Thursday, we'll meet in a Zoom meeting to kind of discuss feedback and how everybody's doing. And then we'll move into problem solving dealing with lenses.